we're going to consider the following function f of x equal to x cubed minus 12x. And our goal is to eventually get a sketch of this graph by using what we know about the first and second derivative. So we're going to begin by finding the first and second derivative. So f prime of x is equal to 3x squared minus 12. And then taking the derivative of the first to get our second derivative, we have 6x as our second derivative. Now we're asked about the domain. The domain of f prime, and f double prime is all real numbers, negative infinity to infinity. Because if we look at all three of these functions, they are polynomial functions, so the domain of all three functions are all real numbers. Next, we're asked to find the critical values of f. Critical values are where the derivative is equal to 0 and where the derivative is not defined. Since the first derivative is a polynomial function, it's defined for all real numbers, so we're just finding where the first derivative is equal to 0. So setting 3x squared minus 12 equal to 0 and solving, we can factor out a 3. So we're left with x squared minus 4 equal to 0. Solving for x, we have an x squared minus 4 equal to 0 when we divide both sides by 3. Adding 4 to both sides, we have an x squared equal to 4, and then taking the square root of both sides, we get x equal positive or negative 2 as our critical values. Just so that we have the function values later, let's go ahead and plug negative 2 and 2 both into the original function to get the outputs for these x values. So if we plug a negative 2 into our function, we have a negative 2 cubed minus 12 times a negative 2, which simplifies to give us a positive 16. Then if we plug a positive 2 into our original function, we have 2 cubed minus 12 times 2, which gives us a negative 16. So our two critical points then are negative 2, 16 and positive 2, negative 16. Next, we want to state where the function is increasing or decreasing and any relative extrema. So we can use our second derivative test to determine whether our critical values are relative maximums or relative minimums. So we can take our second derivative and first plug in our critical value negative 2 into the second derivative. Recall that the second derivative is 6x. So we have a 6 times a negative 2, which gives us a negative 12. So since the second derivative is negative, it is less than 0, we have a relative maximum at x equal negative 2. Next, we can take and plug our critical value positive 2 into the second derivative. So we have 6 times 2, which is a positive 12. So since our second derivative is positive, we have a relative minimum at x equal 2. So now to determine intervals of increasing and decreasing, let's think about what's going on at each of our relative extrema. We have a relative maximum at x equal negative 2. So if we have a relative maximum, then that means our function is increasing before we hit the maximum and then decreasing after we hit the maximum. So prior to x equal negative 2, that would be on our x-axis, that would be from negative infinity up to negative 2. So we are increasing from negative infinity up to negative 2. And then after we hit our maximum, our function is then decreasing. So we are decreasing from negative 2 up until our next critical value, or our next relative extrema, which occurred at positive 2. So we are decreasing from negative 2 to positive 2. And then at positive 2, we have a relative minimum. So after we hit that relative minimum, we are decreasing, we hit the relative minimum, and then our function has to increase again. So then we are increasing for the remainder of the function. So we are increasing from a positive 2 to infinity. So we have our intervals of increasing and decreasing, and then we know that our relative maximum, it occurred at negative 2, and we already found what that maximum value is. It is 16. We found that in part B. And then our relative min occurs at x equal 2, and we found what that relative minimum is. It is negative 16. Next, we want to list the coordinates of any possible inflection points. Recall, inflection points are where a graph changes from concave up to concave down, or concave down to concave up. It's where it changes concavity. And we find those by looking at the second derivative. Inflection points we find by looking at where the second derivative does not exist and also where the second derivative is equal to 0. Since our second derivative is a polynomial function, recall that we found the second derivative in part A to be 6x. Since that is a polynomial function, it is defined for all real x values. So we're just looking at where the second derivative is equal to 0. So setting 6x equal to 0 and solving for x, we get x equal to 0. Let's go ahead and plug this x value back into the original function so that we have the following corresponding output in case we want that information later. So we plug 0 into the original function. We have 0 cubed minus 12 times 0, which gives us 0. So the point 0, 0 is a possible inflection point. Next, we want to state where the function is concave up or concave down. So a function will change concavity at an inflection point. So what we need to do is we need to evaluate what is happening around our inflection point. So we're going to divide our x-axis up into two intervals around our inflection point, which was 0. So we're dividing the x-axis into 0, negative infinity to 0, and then 0 to infinity as our two intervals. And we want to know what's happening to our second derivative in each of these intervals. So we will use our second derivative to test for concavity. So let's pick a value out of our first interval, negative infinity to 0. For example, I could choose a test value of, say, negative 1. If we plug negative 1 into our second derivative, we get that the second derivative is negative. A 6 times a negative 1 is a negative 6. So our second derivative is less than 0. Since our second derivative is negative, it means that we are concave down on this interval. Next, let's pick a test value out of the next interval, 0 to infinity. For example, we could choose a test value of 1. If I plug 1 into our second derivative, so we have a 6 times 1, which is a positive 6. So here our second derivative is positive. Since our second derivative is positive, it means that we are concave up on this interval. So next we're going to use this information that we've gathered so far in parts A through E to sketch a graph of the function. So let's begin by graphing our relative extrema. So our relative maximum was at a negative 2. So at negative 2, 16, we had a relative maximum point. And then we had a relative minimum at 2, negative 16. So at 2, negative 16, we had a relative minimum point. Next, we can graph our inflection point. We found our inflection point to be 0, 0. Now, when we tested for concavity, we found that the graph is concave down from negative infinity to 0, and then we switched to concave up from 0 to infinity. So based on what we have so far, we can get a general idea of what the graph looks like. We know we have a relative maximum at x equal negative 2, and we have a relative min at x equal positive 2, and we know we change from concave down to concave up at the origin. So based on what we know, we can go ahead and start to sketch the graph, and then I'm going to choose a couple test points to plug into the original function. So I'm going to choose, say, x equal negative 4, and then maybe positive 4. If we plug those into our original function, so we take a negative 4 cubed minus 12 times a negative 4, we end up with negative 16. If we plug positive 4 into the original function, we have 4 cubed minus 12 times 4, which gives us a positive 16. So here are two additional points that can help us with graphing. So I can plot the point negative 4, negative 16, and then positive 4, positive 16, and then connect our graph through those points. And there's our graph of our function.